Alright, so now what we're going to do is we're going to take this application to the next level, which is to create some 2D AVO synthetics, which really is the intent of the software to begin with. What we're going to do is we're going to start with a well log that we've already brought in. We've cleaned up the data. We've got it plotted the way we like. We've identified some hydrocarbon zones, and I'm going to zoom in to the area down toward the bottom of this well where we've defined a gas zone here based upon our neutron and density porosity values and resistivity. We've created a sand volume curve so we know the sand content is a function of depth, and we know the P wave and shear wave velocity. So now what we're going to do is we're going to take this model, and we've got it prepped exactly how we want to do. We're going to now create some amplitude versus offset synthetics. So what we're going to do is we go up to the top this to the menu bar. We have model, and we have two options right now. One is 2D AVO synthetics for the in situ, which would be the well log as defined with the hydrocarbon zones as defined. And the other option is to do a fluid substitution on the in situ, and we would compare the two synthetics side by side, one with the gas in this hydrocarbon zone for this particular example, and one next to it in which we've substituted out the gas for, say, water or oil, or a different level of water saturation with the gas if we wanted to. But for right now, what we're going to do is we're going to start with just the 2D AVO synthetic in situ. Now, when we click on this, we're going to pop up another window, and the size of the window may vary depending on the size of your computer. What I like to do is stretch it out a bit. And then you're going to notice that we've got a single set of AVO traces here, and it tells me at the top that this is the primary response for the in situ, and we're looking at the total response. We'll get into the various components that we can look at later. We also have some of the key curves shown on the left-hand side from the well log. We have the P wave, a density, shear wave, and a sand volume. Now we can customize the layout a bit. We can slide. There's a little bar in the middle. We can slide it to the left, and that opens up, displays a little bit more of these curves. And then we can also change the trace spacing over here. And there's a little ruler in the toolbar up here that says increase traces per inch, which actually puts the trace curves closer to each other, or decrease it, which opens it up. And I'll hit decrease, and you can see how it's opening up. So we'll just leave it at this right now. We can actually close our window so we get it looking exactly how we want it. Now the nice part about this is when I close it and reopen it, or I've saved this project file, all those changes I've made are kept available. So let's get familiar with what we're looking at right here before we get into the details of changing things around. As I mentioned, we have by default the P wave, the density, the shear wave, and the sand volume. Now these are taken directly off of the well log data that we defined as we imported the LAS file and set up the data. And just like before, we can click on any one of these. So if I put the mouse over the P wave and it's telling me it's currently going from 4,000 feet per second to 16,000, I can click on that and I can change some of the parameters of it. I can tell it to use it in thousands of feet, and I can tell it to auto scale or not. But if I do that, now I'm at P wave times 1,000, 4 to 16. And I'm going to do the same for the shear wave, make that times 1,000. And there we go, from going from 0 feet per second up to 10,000 feet per second. So that's how we, very simple, set those well log charts. Now we also have zoom controls up here, just like we've had before. So I click on the dynamic zoom, which is the more useful. I can click anywhere on this and drag, and we'll zoom in to whatever level we want. And if you have a mouse wheel, you can scroll up and down. Now I'm going to zoom out a little bit by hitting the zoom out icon at the top, back to a reasonable level. Now one thing you will notice is that the scales that we're showing here, we show this in true vertical depth. So if you have a deviation survey that's been pulled in with the file, that's been applied, and we then show the true vertical depth here. Then we also show the time in seconds on the same scale so that you can see where things are from a time perspective. Now you'll notice in the synthetic traces over here, we're plotting everything as an offset distance and not the angle. However, we are drawing the angle curves over the synthetics, and we can change those on the level of granularity that we want to show with those without any problem. So with that, we now have this curve here. Now we have, one of the first things, again, people say is how do we change the colors? We'll get to that. That obviously can be changed. So when we look at the traces, we're looking at a zero offset on the far left, and we see the trace as a function of time, but we also overlay the depth here so you can see that. And that goes all the way out. We're doing this case at 500-foot increments all the way out to 12,000 feet of offset. All those parameters can be changed, the increment, the number of steps to meet the parameters of your well. Now we also show the stack trace over here. Currently we're going from 0 to 30 degrees, and we can change that offset, that stack angle if we like. And then we're showing intercepting gradient, in this case the NIP and the B, and we're showing those traces. One other thing I want to show you is that we've got the wavelet here, and this is the wavelet that we've defined that's taking the reflection coefficients computed from the well log and then eventually producing all these traces. And we show the wavelet on the same time scale that we have our synthetics drawn in, so that you can see very easily that this is the normalized wavelet that we're applying to it. If you want to know what the properties are of the wavelet, we can look right above here where it says this is a Gabor wavelet. We're looking at the sine component, 30 hertz. We have a damping ratio. We have 0 degree phase shift on it, and sample rate, and the number of points. Now, if we click on that, we could change the wavelet, but we're not going to do that right now. So this is what we're doing. We've taken this model, we've identified that we have gas in this hydrocarbon zone, and we put it over here. Now, the one thing you might also focus on are these cross plots down at the bottom. Now, these also have a bar here, so I can make this bigger if I want. Okay, so what I've done is I've dragged this up to make these cross plots a little bit larger. Now, on the left-hand side, we have layer attributes, and these are cross plots of attributes, key attributes, as a function of depth. So we can see that these are the layer attributes from 8,660 feet to 8,788 feet. Well, how did we get that range? Well, we have this shaded rectangle over here, and you can see it on both the time scale as well as on the depth scale. Now, on the depth scale, we're saying we're going this area of interest, this zone of interest, I like to call at times the focus zone, is going from 2.4 seconds to 2.429 seconds. And we also have boundary attributes, which are some of the intercepting gradient properties drawn below here. And so we have the NIP and the B, the Poisson's reflectivity versus NIP, NIS, and then the delta mu rho over mu rho plotted versus delta lambda rho over lambda rho. So we can see that, and we can see that data. And that data is pulled exactly from these traces over this range from 2.4 to 2.429 seconds. Now, if we want to change that range, there's several ways to do it. One is we can just grab the end of it and drag it up, and you'll see the time scale moving. You also, if you look to the left, you'll see the depth moving. We always keep the depth and time in sync, even to the point when you're moving your mouse around. And if I'm at 2.35 seconds on the time scale, I can see that my mouse line is shown at the same point on the depth scale. So that way it's always very nice and easy to correlate between the depth and the time scales. Now, the other final plot I want to kind of show you here in the layout is what we call the root mean square plot. And so what we're doing is we're looking at the magnitude as a function of offset over this time range, so we can see how that value changes as a function of offset. In this case, it's fairly constant. When we get to the fluid substituted approach of it, we'll take this gas zone and put, say, water in it, and we'll have side-by-side synthetics so that we can make a comparison between the responses for both the in situ and fluid substituted case. All right, so I'm going to stop this video at this point. This is just an introductory. Here's the layout of what the synthetics look like. And if you have yours, I suggest popping one up when you get to this point and just explore the layout and get comfortable with the layout. And then what we'll do is we'll look at how do we change a lot of the settings, the display, and so on and so forth. And we'll also look at how do we produce output, such as segue output and the like.